Hello, welcome back, people. I hope you all are doing great. So, finally, we are here on the last topic of this module, resampling methods. So, we have covered so far introduction to modeling, linear regression, logistic regression, decision tree, naive Bayes, and multinomial and ordinal logistic regression. Believe me, guys, whatever we have covered so far is a lot of content. We broke it down into small chunks and we have covered many things one by one. If you check out any book, this will easily run into hundreds of pages. Now let's see what we are going to cover in resampling methods. So we will first see what is resampling method, then we will learn cross-validation. We came across this term many times in our previous discussions. So now we'll see this in detail. And after this, we'll do an assignment in R on cross-validation. Okay, then let's start now with our first topic, resampling methods. So in resampling methods, we repeatedly draw samples from the data and build model on each of these. That is why it is called resampling. We are doing sampling over and over again. Now cross-validation and bootstrapping are few common methods of this approach. We already know what bootstrapping is. In bootstrapping, we generate B new samples from our data and create B new models to ascertain the variability among these models. However, in cross-validation, we use the approach of splitting the data into training and test part. And then we use the training data to build the model. Once our model is built, then we use the test data to calculate the test error rate. We are always interested to know the performance of our model on the unseen data, that is our test data. The training error will always be less than the test error because the model was built on the training data. So obviously the error will be less. So in this way we ascertain the accuracy of our model using cross-validation. So the first approach in cross-validation is validation set approach. It involves randomly dividing the available set of observations into two parts, a training set and a validation set or holdout set. Let's say we have divided this in 70:30 ratio. We could divide this in any other proportion as well, but for now let's assume 70:30. Now we'll build our model on training data and then calculate MSE for regression or classification error rate for classification from the test data to know the accuracy of the model. However, there are few drawbacks of this approach as well. The first drawback is that depending upon which observation is included in validation set and which is not, the validation error could be highly variable. Second drawback is that we use only a subset of the observations to train the model. And for training models, the more data, the better it is. Statistical models perform worse if they are trained on fewer observations. Now to overcome these issues, we modified this approach to leave one out cross-validation, which is our next approach. Like the validation set approach, leave one out cross-validation involves splitting the dataset into two parts. However, instead of creating two subsets of comparable size like we did earlier as 70:30, here a single observation is used for the validation set, and the remaining observations make up the training set. As you can see here, only one observation is kept for testing the data and rest are part of the training data. Then we perform this process throughout our data by keeping one observation for validation and rest for training. Once we apply this process on the entire dataset, we then average the validation error MSE or classification error rate to assess the model accuracy. Since we are keeping only one observation out, hence this method is called as leave one out cross-validation. Now the main advantage of this method is that we use almost all the data in the entire process, and hence leave one out cross-validation tends to not overestimate the test error. However, the drawback of this method is that it is computationally very slow, as we have to go through all of the data set. Hence, we further modified this to k-fold CV, which is our third approach for cross-validation. Now, this approach k-fold CV involves randomly dividing the dataset of observation into k groups. These k groups or k-fold are of approximately equal sizes. As you can see, the first fold is treated as a validation set, and the model is fit on the remaining k-1 folds. After that, we take the average of the validation error MSE or classification error rate to assess the accuracy of the model. The main advantage of this method is that it is computationally efficient. It also addresses the drawbacks of our first method validation approach, which was issue of variability in test error and using a small subset of data for training the model. Now for computational efficiency, we generally use folds k is equal to 5 or 10. So that was all about cross validation. Alright guys, so that is all from resampling methods. It was a quick one, but a very important topic. So in this video, we have understood what resampling methods are. Then we saw different cross validation methods. And now let's see how these things work in R. And guys, with this, we are done with module 3. And I hope you can see the difference in your understanding. And in fact, you could see that these things are not very difficult. I mean, obviously there is no end to the learning, but you can develop a very good foundation if you use the correct approach. And this way you don't find them confusing at all. Now, if you take any book, these things that we have covered in our 3 modules, if you put them together, will run into at least 500 pages, if not more. So we actually have covered a lot. So let the ship sailing now. All the best for the next module, where we will see some advanced modeling techniques. So now let's just straight jump into the assignment for cross validation.